So think about the last time you tried to fix a broken coffee mug, or maybe like a piece of plastic trim on your car, and you had to reach for the super glue,
Oh, yeah. We all know exactly how the story goes.
right? You carefully line up the broken pieces, you squeeze that tiny rigid tube, and inevitably a drop escapes.
And you end up getting it right on your fingers.
Exactly. Suddenly your skin is basically welded together, the glue hardens into this rock-solid crust, and you're frantically scrubbing your hands at the sink trying to get it off.
It is the absolute worst.
It really is. Or, on the flip side, maybe you bought one of those heavy-duty adhesive hooks to hang a wet towel in your bathroom.
Oh, the ones that claim they hold like 20
Yeah,
pounds.
those. Just stick it onto a completely smooth tile. You press it incredibly hard, and the second you actually hang something on it, you just watch it slowly, agonizingly slide right off under pressure.
Just taking a patch to the wall with it, usually.
Right. It is universally frustrating, and it really highlights a massive contradiction we just accept in our everyday lives. Welcome to the Deep Dive Lab, by the way.
Thanks. Yeah, we interact with adhesives constantly, right? From the tape on a shipping box to the microscopic glue holding the screen of the device you are listening to right now.
But they always seem to be either way too permanent, like ruining whatever they touch, or just completely useless when we actually need them to hold any weight.
Which is exactly what brings us to the strange mystery question for this deep dive.
Yeah, here's the strange question for you guys today. Why is it that the stronger a glue is, the harder it is to remove? And conversely, why does practically nothing stick to certain surfaces like, say, Teflon?
It's honestly one of the most persistent, annoying problems in material science. But scientists have finally cracked a seemingly impossible molecular code to solve this exact issue.
Wait, really? They actually solved it?
They did. They've essentially created a holy grail material, an adhesive that completely defies all the conventional rules we thought we understood about how things stick together,
Oh.
and, more importantly, how they come apart on command. So our mission today is to explore exactly how this breakthrough happened, because it really rewrites the playbook on how humans manufacture things.
Okay, I am so ready for this. But before we get into the actual breakthrough, let's look at the villain of our story. You mentioned scientists were fighting against conventional rules. What exactly is the core problem that makes creating a perfect glue so difficult in the first place?
Right. So in material science, researchers have spent decades banging their heads against something called the strength-ductility trade-off.
The strength-ductility trade-off. Okay.
Yeah, to put it simply, strength and ductility are basically natural enemies. They are diametrically opposed properties.
So you can't really have both at the same time?
Exactly. Strength is a material's ability to resist being pulled apart or deformed when you put it under stress. Ductility, on the other hand, is a material's ability to stretch, flex, and dissipate energy without suddenly snapping or shattering.
Wait, so if I'm picturing this right, it's kind of like pasta.
Pasta. Okay, go on.
Hear me out. If you take a handful of uncooked spaghetti, it's highly rigid. If you try to compress it end to end, it transfers stress very effectively. Like, it's incredibly strong.
Right, but it's entirely brittle.
Exactly. The second you apply bending pressure, it snaps violently in half. That's a strong but non-ductile material, like a heavy-duty commercial epoxy.
That is a perfect analogy, actually. And to take that spaghetti analogy further, think about the opposite end of the spectrum.
Cooked spaghetti.
Yeah, cooked spaghetti. Ductile adhesives, like the sticky gummy part on the back of packing tape, are just like cooked spaghetti. If you pull on it, it stretches, it bends, and it can absorb a lot of movement.
But it's weak. You can pull a wet noodle apart with almost zero effort.
Exactly. The trade-off exists because of the molecular structure required for each physical property. To get structural strength, you need rigid, highly cross-linked molecules that lock firmly into place.
But to get the stretch, the energy dissipation, you need molecular mobility.
Right. Molecules can't be rigidly locked and freely moving at the exact same time. It's just physics.
Right. You can't be uncooked and cook spaghetti simultaneously.
Yeah.
So how did scientists traditionally try to solve this? Did they just try to mix the two together?
They tried, definitely, but for a long time, the absolute rule was that to achieve tough adhesion, which is that rare, magical combination of being both highly strong and highly ductile, you strictly needed a polymer.
Okay. And polymers are the really long ones, right?
Yeah, polymers are massive, incredibly long chain molecules. The idea was that if you have these giant chains, they can entangle with one another.
Yeah, like a massive tangled bowl of that cooked spaghetti.
Exactly. The sheer length and tangling provide a rigid framework for strength, but there's just enough slack in the tangled mess to stretch and absorb a shock before it finally
That
breaks.
would make sense.
But because of this, scientists assume that small molecules, which are vastly shorter, were completely useless for tough adhesion.
Because they just wouldn't have the length to form a safety net, right?
Right. The assumption was simply that small molecules are like macaroni. They are too short to physically tangle, so they could never provide the necessary stretch and strength. They'd just pull apart.
Okay, so that's the structural problem of the glue itself. But that's only half the battle, right? Because the other half is the surface you are actually trying to stick this glue to.
Oh, absolutely. And in the world of adhesives, there is a boss-level surface that defeats almost everything we throw at it.
Polytetrafluoroethylene.
Hmm.
Or, as practically everyone knows it, Teflon.
Yes. Teflon, or PTFE, is notorious in the chemistry world. I mean, it is technologically vital. It's used in medical implants, aerospace engineering, and of course, frying pans.
Right. My eggs slide right off it.
Exactly. But its surface is highly inert. It has an extremely low surface energy. In practical terms, this means it is incredibly difficult to bond to anything.
Why is that, though? What makes it so slippery at a molecular level?
It comes down to fluorine. The Teflon molecule has a backbone made of carbon atoms, but that carbon is entirely surrounded by tightly packed fluorine atoms.
Okay. And fluorine is sticky, slippery.
Well, fluorine is highly electronegative, meaning it hogs electrons. It essentially creates this slick, impenetrable armor of negative charge around the molecule that aggressively repels other molecules.
Oh, wow. So it's basically pushing everything away.
Yeah, it's like a phalanx of Roman soldiers with their shields locked together. Nothing gets in, water beads up and rolls off, oils slide away, and commercial glues literally just peel right off like old sunburned skin.
Ew. But okay, I get the picture. So this brings us to the actual discovery, because a team of researchers out of Japan working across the University of Tokyo and Riken just shattered all these rules.
They really did. The team, led by Dr. Takuzo Aida, Kohei Kakawa, and Abir Goswami, published a study in the Journal of the American Chemical Society that is just mind-blowing.
They basically created a glue that shouldn't exist, and they stuck it to a surface that nothing sticks to.
Exactly. They introduced a completely novel molecule that shatters the old paradigms. It is called cyclic FP phenamok.
Okay, cyclic FP phenamok. That is a mouthful. Let's translate that for everyone listening. What actually is this thing?
Well, chemically speaking, it is a fluorocrown ether phosphate.
Still a mouthful. Let's break that down into plain English.
Fair enough. The structure is the secret to everything here. First, it is a small molecule. It is not a massive, entangled polymer chain. It's a tiny, isolated unit.
Okay, so it's the macaroni, not the spaghetti.
Yes, exactly. Then, the fluoro part means it contains fluorine atoms. The crown ether part means a section of the molecule is shaped like a little ring, or a crown.
Got it. And the phosphate part.
That is a specific chemical group often used to bond to metals and minerals.
Okay, and we should probably clarify right away, because whenever people hear the words fluorinated chemicals, they immediately think of, like, toxic runoff in rivers and forever chemicals. Is this stuff dangerous?
Oh, that's a great distinction to make. Cyclic FP phenamok is completely safe for the environment. It is explicitly not a toxic PFAS, or what the media calls a forever chemical. It was engineered to be safe.
Oh, that's a huge relief. Okay, so the researchers have this new non-toxic small molecule. Looks like a little chemical ring. And they decide to test it against the ultimate Boston-treated Teflon plates.
Yep.
Tell me about this experiment, because I'm picturing a highly complex, pressurized, superheated laboratory setup.
That's the craziest part. The beauty of it is how shockingly simple it was. The researchers just took this small molecule powder, melted it down slightly, and sandwiched it between two completely untreated, uncleaned pieces of Teflon.
Wait, untreated? They didn't rough up the surface with sandpaper to give it grip?
Nope. They didn't use harsh chemical primers to eat away the armor either. They literally just sandwiched the melted adhesive between the slick plates and left it sitting on a table at room temperature for exactly 10 minutes.
Just 10 minutes on a table. And then they tested the strength.
Yeah. They hung a weight from these two glued together Teflon plates. And keep in mind, the contact area where the glue touched the plates was just 7 square centimeters.
That is, what, roughly the size of a large postage stamp?
Exactly. On that tiny, super slippery surface, this small molecule adhesive held an 8-kilogram weight.
Wait, 8 kilograms. That is nearly 18 pounds dangling from two pieces of Teflon, held together by a tiny square of a small molecule that isn't even supposed to be strong.
I know, it's staggering. In their rigorous lab shear tests, which is how engineers measure the exact mechanical stress required to pull adhered surfaces apart, cyclic FPFAG achieved a tensile stress of 1.3 megapascals.
Okay, 1.3 megapascals. Most of us don't speak in pressure units, so what does that actually feel like in the real world?
Well, 1 megapascal is equivalent to about 145 pounds of force pulling on a single square inch. So 1.3 megapascals is roughly equivalent to a large adult man hanging by one hand from a surface the size of a quarter.
Oh, wow. That is insane.
And to really appreciate that number, we have to look at the competition. The researchers tested standard heavy-duty commercial adhesives like epoxy, acrylic, silicone, and urethane glues on the exact same Teflon plates.
And how did they do?
Those commercial heavyweights only managed a measly 0.1 to 0.7 megapascals before they catastrophically failed and peeled off.
So this tiny molecule completely blew them out of the water. It nearly doubled the strength of the absolute best commercial superglue.
It did.
Okay, hang on. I need to stop you there.
Yeah.
Because this physically doesn't make sense to me.
What do you mean?
You just spent 5 minutes telling me that without massive tangled polymer chains, a glue will be brittle and snap. But now you're telling me this short, small molecule, the macaroni from our analogy, held almost 18 pounds and didn't shatter. If it doesn't have the long, tangled chains to absorb the stress, what on earth is holding it together?
That is the core of the mystery, and the answer lies in something called dynamic non-covalent interactions.
Dynamic non-covalent interactions. Okay.
Yeah, cyclic FPFAG achieves a massively high work of debonding measuring at 1,300 newtons per meter. For context, pulling apart heavy-duty Velcro takes about 100 newtons per meter.
So this is like 13 times harder to separate than heavy-duty Velcro.
Exactly. But it doesn't achieve this through physical, permanent tangles. Instead, it relies on a highly orchestrated network of reversible chemical interaction.
Reversible, like invisible magnets.
Yes, exactly like invisible magnets. Specifically, it uses 3 different types of magnetic attractions simultaneously.
Okay.
First, it uses FF interactions, which are fluorine atoms on one molecule magnetically attracting fluorine atoms on another. Second, it uses hydrogen bonds, which is how water molecules stick together.
Okay, and the third?
And third, it uses what chemists call pi-p stacking.
Pi-p stacking. I know we're not talking about baking pies here. What is that?
Yeah, definitely not pies. Remember how he said part of the molecule is shaped like a ring?
Right, the crown part.
Exactly. In chemistry, certain flat, wing-shaped molecules have clouds of electrons floating above and below them. When you stack these flat molecules on top of each other, those electron clouds interact and stick together.
Oh, interesting.
Think of it like taking 2 wet, flat dinner plates and stacking them. When you try to pull them straight apart, they aggressively suction together.
Okay,
right?
you have to slide them apart usually.
Yeah.
So that's similar to pi-p stacking.
Exactly.
Okay, so instead of a physical tangled knot of long plastic strings holding the material together, it's more like millions of microscopic invisible magnets and wet dinner plates holding hands.
That is a very vivid way to put it, but yes.
And when the glue is put under stress, these magnetic bonds break to absorb the shock. But because they're still magnetically attracted, they instantly snap back together to dissipate the energy.
Precisely. It is a highly dynamic, living system. The researchers actually performed stress relaxation tests to prove this.
What did they find?
They found that when severe stress is applied, the internal structure of the adhesive relaxes and reconfigures itself in just 60 milliseconds.
Wait, 60 milliseconds? A blink of an eye takes about 300 milliseconds. So this glue is breaking and healing itself 5 times faster than a human can blink.
It's incredible, isn't it? That incredibly rapid breaking and reforming acts like a microscopic shock absorber. It allows the small molecules to stretch and absorb massive amounts of energy without violently fracturing.
Okay, that perfectly explains how the glue holds itself together. But how does it stick to the Teflon armor?
Well, the researchers used atomic-level scanning techniques, essentially an MRI for molecules, to peer down at the surface. They proved definitively that the fluorine atoms within the adhesive molecule were actually interacting directly with the tightly packed fluorine atoms on the notoriously inert Teflon surface.
Oh, wow. So it was using Teflon's own slippery armor against it? It bonded fluorine to fluorine.
You got it.
But wait, I have a logic question here.
Okay, shoot.
You just said it uses its own fluorine to magnetically attach to Teflon's fluorine. But earlier, in the research notes, it said this stuff also works on glass, stainless steel and polypropylene plastic.
It does.
Glass doesn't have fluorine armor. Stainless steel doesn't have fluorine. So how on earth does a fluorine-seeking magnet stick to a glass window?
That is a fantastic catch, and it's exactly why this molecule is considered a holy grail. Remember the full name we translated earlier? Fluorocrown ether phosphate.
Right?
The fluoro part is the tool that handles the Teflon, but the phosphate and the crown ether parts are entirely different functional groups. It is essentially a chemical Swiss Army knife.
Oh, so it has different tools for different jobs.
Exactly. When you put it on glass or metal, the fluorine part might not have anything to grab onto, but the phosphate group swings into action. Phosphate is incredibly good at forming hydrogen bonds with the silicon and oxygen found in glass or the oxidized surface of metals.
That is brilliant. The molecule just adapts to whatever surface it's touching, using whichever tool in its structure fits best.
Exactly. It's a universal adapter for adhesives.
But that brings us to the biggest question of all. We have a small molecule adhesive that rivals industrial epoxies.
Yeah.
It acts like a shock absorber to survive impacts, and it bonds directly to almost any surface on Earth, including Teflon.
Yep.
If it's this incredibly strong and essentially fuses with these materials, isn't it stuck forever? Haven't we just created the ultimate permanent super glue that we will never, ever be able to remove?
And that is exactly where the research team delivered the final, most important twist of this entire study.
Oh, thank goodness. What is it?
Because cyclic FP-FOC relies entirely on those dynamic reversible interactions through microscopic magnets, instead of permanent, covalently cross-linked polymer networks, it has a built-in easy wipe-off feature.
What do you mean by wipe off? Like with a harsh chemical solvent?
Nope, just common ethanol, regular alcohol.
Wait, really? Just alcohol?
Alcohol. If you apply a few drops of ethanol to the bond, the alcohol molecules rush in and interrupt all those microscopic magnets. The PP stacking, the hydrogen bonds, the fluorine attractions, they all just temporarily let go.
That's wild.
The adhesive simply releases its grip, and it can be completely wiped off the surface like dust. It leaves absolutely zero trace of residue behind.
That is staggering. A glue that holds 18 pounds on a postage stamp of Teflon, but washes away completely with a splash of rubbing alcohol.
It gets better, actually.
How could it get better?
Because the molecule itself isn't chemically destroyed in this process, you can collect the wiped-off adhesive, let the alcohol evaporate, and reuse the exact same cyclic FP foam adhesive more than 10 times with literally zero loss in its 1.3 megapascal strength.
Okay, which perfectly leads us into the broader implications here. Because while sticking things to a slippery frying pan is a great party trick, the impact of this goes way, way beyond nonstick surfaces. We are talking about fundamentally changing how human beings manufacture and recycle technology.
We absolutely are. I mean, we currently live in a world governed by permanent adhesives, and it is a massive driver of the global e-waste crisis.
Oh, for sure. Think about the devices we use every day. One of the single biggest hurdles to recycling modern technology, whether it's a smartphone, an electric vehicle battery, or a complex medical device, is the glue.
Right. We weld these components together with robust, rigid, polymeric adhesives that are basically designed to be permanent.
Yeah, like when your phone battery dies, you can't just open the back and swap it out anymore. The battery's glued to the casing with industrial adhesives. If you pry it wrong, the lithium-ion battery can bend and literally catch fire.
Exactly. When that device reaches the end of its life, or if just one tiny component breaks, you can't unglue it safely. The materials often have to be shredded, chemically burned, or just thrown into a landfill, which wastes precious metals and rare earth elements.
Imagine how this applies to your everyday life. Imagine a world where you drop your smartphone and the glass screen cracks.
A nightmare for everyone.
Right now, repairing that is a nightmare for technicians. They're using heat guns and metal pry tools, often breaking the internal components further just to defeat the glue.
But with a material like cyclic FP FOMOC,
A repair technician can simply apply a few drops of ethanol to the microscopic seam of your phone. The industrial strength glue holding the glass just dissolves and wipes away cleanly.
they pop off the broken screen with zero force.
Right. They slot a new one in and then re-glue the new screen using the exact same adhesive they just wiped off.
It really highlights the sheer elegance of what these scientists have accomplished. By stepping away from massive polymer chains and utilizing non-covalent bonding, those millions of tiny dynamic chemical magnets, they have finally bypassed the strength-ductility trade-off.
Amazing.
They proved you don't need a rigid, permanent plastic to get unbreakable strength. You can get industrial performance from a small molecule that is fully sustainable, fully removable, and infinitely recyclable.
It's a complete paradigm shift. It means we don't have to choose between a product being durable and a product being recyclable anymore.
Exactly.
So as we wrap up our investigation today, what are the three core takeaways you should remember from this breakthrough?
Well, first, scientists have successfully created a small molecule adhesive that completely defies the old rules of material science, proving that you can achieve both extreme strength and extreme ductility without needing a massive polymer network.
Go.
Second, because of its unique Swiss Army knife chemical structure, this molecule achieves unprecedented bonding to practically anything, including the most notoriously stubborn surface on Earth, Teflon.
And the third?
And third, despite its incredible holding power, it can be completely removed without a trace and recycled over and over again using nothing but simple alcohol.
If we connect this to the bigger picture, this fundamentally changes how we view material permanence. I mean, for over a century, human engineering has operated on the assumption that if you want something to be strong and durable, it must also be irreversible.
Right, permanent performance always equaled permanent environmental waste.
But this study proves that assumption completely wrong. We can have ultimate structural integrity during a product's useful life and effortless clean separation the exact moment the life is over.
It is truly a game changer.
It really makes you wonder about the future of how our entire world is put together. If this discovery is just the beginning, what might scientists uncover next? Could the future of all human manufacturing, from our skyscrapers to our spaceships, rely on materials that hold together like iron, but dissolve on command like sugar and tea?
It's definitely something to think about.
Thank you so much for joining us in the Deep Dive Lab today. If you enjoyed uncovering this mystery with us, be sure to follow and subscribe for more fascinating science stories as they unfold in real time. Until next time, keep questioning the world around you.